So there's a bunch of new faces in here since I made this announcement before, so it's worth repeating, and I'll be honest, you're going to hear this about 5 more times today. Be very careful with your coffee. If you spill it on the laptop, you buy the laptop, which is rather expensive, and we have had this happen before. Especially during the tutorials, we have to walk between the desks to help you out, and things get bumped and so on, so just be careful, drink fast, whatever works. So I'm going to talk a little bit about some basic terms in FreeSurfer that we use. You may be familiar with these terms already. If so, that's great. You know everything, but not everybody uses these terms. We're from all different backgrounds, so I'd just like to get everyone on the same page before we get started, and before Bruce comes in here and just starts going through all of it. So these are the terms I'll go over. And again, if you know them all, then you're all set. I do have a bit of a cough, so I'm sorry if during my presentation I break down for a bit coughing, but Lila will just take over, right Lila? Okay. So, you are all here to learn about FreeSurfer, so you may know this already, but what FreeSurfer is really doing is taking your MP-Rage, or your T1 weighted image, and it's labeling all the different parts, and doing this automatically without much work from you other than you sending a command and saying, do this. And it takes some time, but it definitely doesn't take as long as it would if you did this by hand. So it's great that FreeSurfer goes and does all this, and it labels gray matter, white matter, subcortical structures, different cortical regions, everything for you, and computes the stats for every subject you give it. So we're going to refer to voxels. Voxel is basically a pixel. In this image, pointing to a square there, that's the pixel. It's called a voxel here because it actually has volume. This is a 3D cube, and the MRI images are made up of all these voxels, and that's how we get some of our first measurements, right? They have a volume. We can add up all the voxels within this brain and know the volume of the brain. You'll hear us talk about surfaces, and whenever we describe a surface, we are talking about these boundaries, and more specifically, the boundary between white matter and gray matter, and the boundary between gray matter and cerebrospinal fluid. In this picture, the red line is the boundary between CSF and PO and gray matter, and we'll call it the PO surface. And the yellow line is the boundary between gray matter and white matter, and we'll refer to it as the white surface. So, you'll hear Bruce and other speakers just saying white surface, PO surface. This is what we're referring to. Now, when we talk about surfaces, you have to think of it in 3D. So I'm showing you one slice zoomed in here. That's a 2D slice. But if you take every slice of the brain and you stack it up, what you're going to have are these images here. So on the bottom, that is the PO surface, if we were to stack all those slices up. And on the top is the white surface, which looks a bit strange, but you can see down into this whole side. Each surface is made up of many tiny points, and these are the vertices. And we'll actually, in our talk later today, explain a little bit more about these vertices and why we use them. But what's important to know is that this is what makes up the surfaces, and this is where we store all of our information, all the different measures that you're going to be interested in later on. We'll also say the word recon a lot. Recon can refer to a couple of different things. We might say, check your recons, and in that case, we're talking about the outputs we got from FreeSurfer. We might say recon your data. We use it as a verb, and that means actually running it through the processing stream. It's short for reconstruction, so it's the cortical surface reconstruction that we're doing. And we just shorten it to recon. You'll hear us throw that term around a lot. Also, the command that runs FreeSurfer is recon-all. And what that's really saying is recon everything, run all the steps, do everything all in one shot. And that's what it looks like. We'll also use the term volumes a lot, and we are usually not referring to the measurement volume. We're usually referring to files. This is an example of several files that we'll call a volume. And these are different outputs from FreeSurfer. Usually they have the MGZ extension and they look like MRI data. So when we say check your volume or bring up your volume, we're probably referring to one of these. Also, just a little anatomy. For those who are not familiar with the brain, we have two different areas that we'll look at here. And one is the cortex, that's the gray matter, and the cortical ribbon gray matter, and then there's the subcortical gray matter. And that's all the different structures like putamen and amygdala and hippocampus. So we'll refer to the cortical gray matter and the subcortical gray matter separately. And here I have circled the subcortical gray matter. And what's important to note here is you might see the surface, see that red surface going through the amygdala. Here's my laser pointer. So you might say, oh, what's wrong with FreeSurfer? The surfaces are not even on the outside of the structures. The surface is really the cortical surface. We use surfaces to measure that cortical ribbon, not to measure the subcortical structures. The subcortical structures are measured by these color maps. So if you see the surface going through the amygdala, that's fine. In the end, we don't take any of the subcortical structures for our total measurement of surface. So if you see something like that that you think doesn't look accurate, feel free to ask us about it. But just note there are some areas where we're skipping over that information. And really it's just that we need the surface to be completely enclosed. So we had to cut through there, but it doesn't count essentially. So the other reason I bring up the cortical ribbon and the subcortical structures is that we use two different terms for how we label them. The subcortical areas, we refer to them as a segmentation. We segment them. We label them different colors and different numbers. And the cortical ribbon, we say that we parcellate it. It's the cortical parcellation. Essentially, this means the same thing. We're dividing them up into different regions. But when we say parcellation, we're pretty much always referring to the cortical ribbon. And when we say segmentation, we're almost always referring to the subcortical areas. So that's pretty much it for my section. That's all the very basics that you need to know to get you through the next couple lectures. But Lila's going to come up and she's going to talk a little bit about these registration terms. So when I say registration, this is more about these MRI images in space, and it can get a little confusing because there are lots of terms for the same thing, and we'll throw them around during the talks. So it's definitely a good thing to pay attention to Lila and see what terms we'll end up using so you don't get lost later on.
So good morning, everybody. As Alison introduced, I'm going to just go through a simple vocabulary. Yes, you can post your questions here. A simple vocabulary for the registration procedure. So registration, or in other words, spatial alignment, is a tool or an algorithm that will allow you to find a common coordinate system for images that you are analyzing. And anytime that you are dealing with more than 2 images that you want to do some kind of analysis on, you want to do some kind of comparison with, you will need to do registration on those data sets. I'm giving 2 examples. So for example, you want to compare MR images of the same individuals taken at different time points. The subject is going to be positioned slightly differently in the scanner, or there might be some anatomical changes, that happened in between those 2 time points. So you definitely want to make sure that when you are comparing different areas, you are comparing the right things. Or when you are comparing MR images of different individuals, let's say you are doing your population studies, you definitely want to make sure that all of those scans are in the same coordinate system. So I'm showing you a very, very simple example here for inter-subject unimodal registration. So inter-subject, that qualifier means that we are looking at two different subjects. Unimodal means that we are using the same modality for imaging the subject. On the left side, you see a target image, and on the right-hand side, the subject image. In this scenario, we are going to apply the transformation to the subject and try to register this subject into the coordinate space of the target. And here in the bottom, I'm showing you three different solutions for the registration. Flirt is the name of the tool that we are using. And here I have a solution with 6 degrees of freedom, 9 degrees of freedom, and 12 degrees of freedom. What this means is that the 6 degrees of freedom includes rotation and displacement. So we have 3 parameters that encode rotation in the 3-dimensional space. So just think about rotating the brain or your image along the 3 different axes that you have. And displacement is just the same thing, but you are just doing displacement along the 3 different axes. When you have 9 degrees of freedom, we add 3 additional parameters. Those are scaling parameters, so you can scale your images along each of the all of your axes. And when you have 12 degrees of freedom, you add shearing component also to your transformation. Let me demonstrate all these transformations with images one after another, so you might appreciate what kind of transformation we apply to the images. So this is the target image. The subject, if I flip back and forth, is clearly visible that they are not living in the same coordinate space. So thus we have to do the registration. So if I apply a 6 degrees of freedom registration, this is the global alignment with displacement and rotations that I get. If I apply scaling as well, you see that there's a slight scaling that's applied further to the brain. And when you apply the 12 degrees of freedom, that there's the shearing movement. So if I click back and forth, this is your final solution between the target and the 12 degrees of freedom. So globally, these brains are aligned, and for some type of application, that kind of accuracy is already going to be sufficient. This is the same demonstration, but just in another view, the axial view. So again, 6 degrees, 9 degrees, 12 degrees of freedom, and this is the type of accuracy that you get with this linear transformation. And again, the sagittal view, here's the subject image. This is 6 degrees of freedom registered version, 9, 12, and this is the global alignment that you get. Now another example, which we are going to cover in this course, and I'm sure a lot of you have data sets, multimodal data sets. So in this scenario, we have same subject, so intra-subject registration problem, and multimodal, which means we get different types of images as input images. So here, in this case, I'm going to do my demonstration with diffusion-weighted images, in particular with an FA scalar map. But you can imagine having your functional acquisition, your PET data, or any other modality, the same would apply here. So again, if you have the same subject but different acquisitions, even if the acquisition happened at the same time, the subject could have moved in between the imaging, or the images might have been taken at different times. So if you want to jointly analyze these images, you need to make sure that they are in the same spatial coordinate system. So on the top, I show you the images before spatial alignment. So here, the red color, I'm just using a different color map for the structural image, just to indicate the displacement or the mismatch in between your input data sets. So if I were to use any measurement taken from my structural data and trying to use it without spatial alignment, you see that I would be comparing nonsensical areas. However, after you do the alignment, you know that there is spatial correspondence in between your data sets, so you can just refer from one spatial coordinate system to another, and you have the right correspondence. The same demonstration, just in another view. Again, before spatial alignment, after spatial alignment, before and after. In this scenario, it was sufficient to use just 6 degrees of freedom. We are using the same subject. The acquisitions were taken on the same day. So we are not expecting any scaling differences in between our anatomy or any kind of shearing. So all we have to control for is displacement and rotation for the images. On the third day of the course, I'm also going to describe to you a more complex registration mechanism. It's a nonlinear registration mechanism called Combined Volumetric and Surface-Based Registration, or CVS. This is a higher complexity registration that morphs your image and gets a much higher accuracy of correspondence in between your images. So depending on what application you want to use or what kind of comparison you want to make in between your subjects, you might need a much higher, much more local correspondence in between your input data sets. So that's what I'm going to talk about on the third day of the course. And that's going to be very useful in order to map both cortical and subcortical labels from one subject or an atlas to the rest of the population that you are analyzing. So very quickly, a quick summary of some registration-related terms. So when you have input data sets, for the most basic scenario, you are going to have two input data sets. We usually use the term fixed template or target, and this is going to be the image that stays fixed, and we are going to be trying to move the moving or the subject image into the space of the target image. We are going to talk about or mention lots of different transformation models. In the previous slides, I introduced you to the rigid one, which is the 6 degrees of freedom in the 3D domain, affine or nonlinear transformations. So again, these terms refer to just different complexity or different types of transformations that you can apply to your images. Objective or similarity functions, we are not going to go into too much detail about this, but it's good to keep in mind that when we do automatic registration, it's basically an optimization problem. So there's an objective function that you need to minimize or maximize. And it's often useful to know what your similarity functions are in order to make sure that the images that you are comparing are best suited by this objective function. If you're interested more in it, please ask me. I can give you more details, but we just don't have time to go over it in this introduction. After you get a registration through your either manual or automatic registration procedure, oftentimes you want to apply that transformation to other images, for example, the segmentation image or an ROI label. When you do that, we use the terms deforming, morphing, resampling, or transforming the data set using those transformation files. And there's also going to be a choice between interpolation types. The two basic ones that you are going to hear about are the linear interpolation and the nearest neighbor. Just a rule of thumb, when you have a segmentation image or a binary image or a mass, you should always use the nearest neighbor interpolation. And when you're dealing with grayscale images, use the linear interpolation. Again, I can give you more details if you're interested. Just raise your hand now, or we can talk about that later. So that's about it. Do you have any interpolation? Sure. So we don't usually go into we don't go into details, but there are two different interpolations that you are going to hear about in some of the tutorials and demos. And so one is the linear one. And as a rule of thumb, you are going to use the linear interpolation when you have grayscale data, or you have your FA volume, your structural data. You would use the nearest neighbor one when you have segmentation, parcellation, or a mass data. Basically, the main difference in between these two is when you are using nearest neighbor interpolation. When you are morphing or transforming your data set, you are not going to be introducing new labels into the resulting data set. So if you started out with a volume that has zeros and ones, in your transferred or morphed volume, you are only going to have 0 and 1 labels also. When you are using trilinear or linear interpolation, that's a more accurate model to transform your data into the new space. However, it does introduce new labels if you happen to be, your voxel happens to be on the boundary of two different ones. So in order to make a smoother transition, it's going to introduce possibly a new intensity value. So this is kind of the basic that you should know. Again, we are going to give some examples. If it's not clear to you, raise your hand and we can give you more examples about that. Any other questions with respect to registration or any of the vocabulary that Alison or I introduced? Okay.